4.3 discusses reciprocal trigonomic ratios. The first reciprocal trig ratio is cosecant. Cosecant theta is equal to 1 over sine theta, or, in other words, hypotenuse over opposite. Secant is the next ratio. Secant theta is equal to 1 over cos theta, or hypotenuse over adjacent. The final ratio is cotangent. Cotangent theta is equal to 1 over tan theta, or adjacent over opposite. The first example asks you to determine the angle given the reciprocal trig ratio. And the trig ratio given is cotangent of C is equal to 5/16. First, notice that cotangent is a reciprocal trig ratio, meaning that cotangent of C is equal to 1 over tan C. From this, we can see that tan C is equal to 16 over 5. If you take the inverse of tan of 16 over 5, that should be the equivalent of C. Therefore, angle C is approximately 73 degrees. The second question asks you to determine two angles between 0 and 360 degrees that have a cosecant of 5. Once again, this question deals with reciprocal trig ratios. Cosecant is equal to 5, which means that the sine theta would equal 1 over 5, or opposite over hypotenuse. Using the cast rule, we can come to the conclusion that because our sine is positive, it could only occur in the S or A quadrants of the cast rule quadrant system. We can now draw the figurative triangles as we know the opposite and hypotenuse sides. Now we can begin to calculate theta. Theta will be equal to the inverse of sine of 1 over 5. Theta is equal to approximately 12 degrees. Note, however, that this is only one of theta's possible measurements. If we take the measurement of theta 2, it would approximately be equal to 180 degrees minus 12 degrees. This second theta could possibly be equal to approximately 168 degrees and would be the angle in the S quadrant. Therefore, the two angles possible are 12 degrees and 168 degrees. 4.4 deals with the ambiguous case, and this section has mostly to do with memorization of the different types of ambiguous case. Case 1, it has one solution. In this case, A is greater than side B, and side A is also greater than the height of the triangle. Case 2 has two possible solutions, B1 or B2. In this case, A must still be less than B. However, A must still be greater than H. This results in two possible scenarios occurring, in which the vertice of B could be connected to B2's length, or the vertice of B could be connected to B1's length. This could create two separate triangles, in which one triangle would have an acute angle and one triangle would have an obtuse angle. Case 3 is fairly similar to case 1, in that it only has one solution. In this case, A is less than B, however A is equal to H, giving a more similar situation to B1 from case 2. Case 4 has no solutions, as A is less than B and A is less than H. When drawn out, this isn't really a triangle at all, which explains why it has no solutions. The question reads, given that A is equal to 6, B is equal to 7, and angle A is equal to 30 degrees, solve the triangle. H is equal to B times sine A, which is equal to 7 times sine 30, which is approximately equal to 3.5. H is less than A, and A is less than B, therefore this question has two solutions. Using sine law, A over sine A is equal to B over sine B. Therefore, sine B is equal to B times sine A over A. There are two angles possible with an approximate sine of 0.5833. These angles are 35.69 degrees and 144.31 degrees. Next, we experiment with the two values. If b is approximately equal to 35.69 degrees, then c is approximately equal to 180 degrees minus 30 degrees minus 35.69 degrees. This is approximately equal to 114.31 degrees. This means that c is equal to 6 times sine of 114.31 degrees over the sine of 30 degrees, which is approximately equal to 10.94. Next, we calculate the other angle value, which would be the angle of b. Calculating this in the same way as angle c, the value will be approximately 5.69 degrees. When we put this into the b formula, it would be 6 times sine of 5.69 degrees over sine of 30 degrees. This is equal to approximately 1.19. Therefore, our two answers would be 10.94 and 1.19. Trig identities are a lot like puzzles. You're trying to prove the equation given to you is true, where the left side equals the right side. For a quick recap, the three types of identities we need to know are on the screen: the quotient identity, Pythagorean identity, and reciprocal identities. You could watch Ms. Nguyen's video on 4.6 for a more in-depth understanding of how these identities are derived. Something to keep in mind while doing trig identities is that you must switch all reciprocal identities into their sine and cos forms if they appear in the question. Notice that cotangent theta can be written like this. When cotangent theta is converted into terms that relate to tan theta, it would be 1 divided by tan theta is equal to cotangent theta. When dividing fractions, you would keep the first fraction as is, then multiply it by the reciprocal of the second fraction. In this case, this would be the answer. Multiplying by 1 doesn't change anything, therefore cotangent theta can also be written as this. It should also be noted that you should use the quotient identity when there is tan theta. Use the Pythagorean identity when there is sine theta plus cos theta. Remember that the Pythagorean identity could also be rewritten. When writing in terms of sine squared theta, it would be 1 minus cos squared theta. When writing in terms of cos squared theta, it would be 1 minus sine squared theta. For the first example, the question asks you to prove that sine theta times cotangent theta plus sine theta times cosecant theta is equal to 1 plus cos theta. Start by making the left side equals right side chart. Next, fill in the part of the equation to its respective side. Looking at the right side, everything already seems to be in the simplest form, so there isn't really much you can do. On the left side, cotangent theta and cosecant theta are still reciprocals, so you could change them into their sine and cos forms. Therefore, cotangent theta becomes this, and cosecant theta becomes this. Notice that the sine theta cancel out. As you can see, the left side is now equal to the right side. Make sure not to forget your therefore statement. For the second example, the question asks you to prove that bracket 1 minus tan theta end bracket squared plus bracket 1 minus cotangent theta end bracket squared is equal to bracket secant theta minus cosecant theta end bracket squared. The right side seems easier to simplify, so you would start there. Apply the reciprocal identities. Since it's a subtraction of fractions, you will need a common denominator. In this case, it is cos theta times sine theta, which is found by multiplying the two fractions' denominators together. The first fraction was multiplied by sine theta to get the common denominator, while the second fraction was multiplied by cos theta. Square the top and bottom. Apply the Pythagorean identity. This side is now complete. On the left side, apply the quotient identity and reciprocal identity. Then find the common denominator and change the numerator accordingly. Square the top and bottom. Notice that there's a cos squared theta and sine squared theta. Apply the Pythagorean identity. Find the common denominator once again, and apply the changes to the numerator. Once again, there's a cos squared theta and sine squared theta. Apply the Pythagorean identity. Factor out the 2 times sine theta times cos theta. This leaves sine squared theta plus cos squared theta in brackets. Applying the Pythagorean identity, it would equal 1. Since the 1 is multiplied, it does nothing to what is originally there. Therefore, the left side is equal to the right side.